Now I want to show you how we can use math or move instruction in our program. So I want to show you some application and how we can place them in our wrong in different situation and how the program will work. The first one is unconditional wrong. So we can use them, they are output instruction. We can use them in a wrong without any condition. So you can see that we don't have any condition here. So it means that in every scan cycle, this instruction will be executed and the addition will happen. So the content of n7:1 will be added to the content of n7:3, and it will be saved at destination, which is n7:5. So this will happen in every scan cycle, and let's assume that your scan cycle is something close to microsecond, then in every microsecond this instruction will be executed and it will save the source. It will add source A to B and save it in destination. Now it might not hurt because the content of source A and B are fixed, and then every scan cycle it just repeats something that is not necessary. It doesn't make any problem for you, but it will increase the scan cycle and it will keep your CPU busy. So it might not be the best situation, but that's an option. So you can use them with unconditional wrong, and in every scan cycle you can do this. Now it might not, there are other options for putting math or move instruction in our program. The second one is optional one. So here you can see that this time if the input is true, then the addition will happen. Now let's assume that after a particular time, for example after pressing a switch, the input will be true and it will remain true. Again, the same thing happens. So after the switch is opened or closed based on the contact type of the switch, as soon as it provides true and provides continuity over this instruction, then what will happen is that every scan cycle this will happen, this will be executed. This is a conditional one, but still it might cause some problem. So in the third scenario, you can see how we can avoid doing this process and performing the addition in every scan cycle. So this time, as soon as you have a true statement here, then OSR, which is a one-shot instruction, will provide a pulse like this because it is looking at this transition from false to true. OSR is a one-shot instruction that works based on rising edge. So as soon as it sees this rising edge, it will provide a pulse, and it means this addition will happen only once because the length of this signal provided by OSR is only one scan cycle. So this will happen once, and then after that it will not be executed anymore until another pulse is produced. So until this go back to 0 and come back to 1 again, so another transition happens here and it will produce another pulse, so this will be executed another time. As I told you, it might not seem to be necessary to use OSR or other type of one-shot instruction. In this case, that you are adding two constant number together and saving the value at destination. But for some application, it is very necessary. I'm going to show you an application. Before showing you the application, I want to show you how it works in other program. So when you're writing a program in any other language, you might have something like this. So x is equal to x plus 2. So this basically means in every scan cycle, you want to add 2 to your variable. So at the beginning, in the first execution, let's assume that your x is 0. The next time, in the next execution, it's going to be 2. The next time, it's going to be 4. So every time that the program is executed, you are increasing your variable x by 2. You can do the same thing in POC as well. For example, let's assume that this is N70, and I want to save the content of N70 added to N71 back in N70. So previously, in the previous example, I was showing you that, for example, we have source A as N70, our source B was N71, and then we were choosing a destination, for example, as N72. So if we are using an add instruction with these addresses, what will happen is that it doesn't matter if you repeat this 1 time or 100 times. Whatever you have in N70 will be added to N71, and the result that you will see in N72 is a fixed number. For example, let's assume that what you have here is equal to 10, and what you have here is equal to 5. So if you add them 1 time, your result at N72 will be 15. If you add them 100 times, that's the same. So if you repeat this process 100 times, that's going to be the same. But sometimes we want to save, basically we want to have an accumulative process. So we want to save the content of the result of this summation back in one of our sources. So let's assume that I change this destination to N70. So this time what happened is that 10 and 15, which are source A and B, will be added together. The result will be saved in N70. So now what will happen is that what I'm going to have here is going to be 15. The next time, so if I executed this instruction 1 time, what I'm going to have in my destination, which is N7:0, is going to be 15. And then if this is executed for another time, what will happen is that this time 5 and 15 will be added together. So what I'm going to have is going to be 20 here. The next time it's going to be 25. The next time it's going to be 30. So every single time that the program is being executed, this value will be increased. Now, that's why you need to make sure in application like this that you are having accumulative process or something like this, when you are having x as x plus a or y as y minus b. So if you're constantly subtracting or adding a value to one part of memory, you have to make sure that the signal that is activating this instruction is not true for more than one scan cycle. Otherwise, you don't know how many times this will be repeated. So you have to make sure that you are using one of those one-shot instructions here. So if you apply the signal like this, only a pulse will be produced here, and a pulse with one scan cycle will only let this instruction to happen 1 time.